Standard physics education treats resonance as a collection of mathematically isolated events rather than a single physical truth. We teach driven resonance as the first silo. This is the Lorentz oscillator, where an external force pushes a system at its natural frequency. We treat parametric resonance as a second, separate silo. This uses Mathieu and Floquet theory to describe how a system becomes unstable when its parameters are modulated at twice the natural frequency. Then we add a third silo for self-oscillation. This relies on van der Pol limit cycles to explain how a system extracts sustained motion from a constant, non-oscillating energy source. Because these phenomena rely on distinct incompatible equations, we are trained to view them as separate physical mechanisms. This fragmentation focuses on the mathematical symptoms of the oscillation while obscuring the unified coherence dynamics that govern all physical resonance. The ODTBT phase strain equation provides the missing link, revealing these three regimes as limiting cases of a single dynamic. First, driven resonance acts as a force-coupled interaction, driving the phase directly while the RCR remains passive. Second, parametric resonance shifts to the coherence channel. The external field modulates the RCR, letting the system extract energy through phase dynamics. Finally, in self-oscillation, the system maintains RCR memory autonomously, drawing energy from accumulated history without an external probe. The twist is the universal mechanism governing the boundaries between these states. It is a qualitative topological bifurcation, a specific moment where the system's phase state triggers a transition into a new attractor. By applying the twist concept, we can finally map resonant behavior as a continuous mathematical spectrum. To understand this unification, look at the flaw in the standard Mathieu equation. Classical theory assumes this parameter modulation is static, that the system has no memory. The ODTBT generalization replaces this with the RCR-modified phase strain equation, introducing the memory term. This RCR term is a dynamical field that evolves as an exponential integral, accumulating the physical strain history of the system. This term ensures that past twist events dynamically alter the damping coefficient. The oscillator literally remembers its past states. The boundary between stability and exponential growth is no longer a fixed line on a graph. A system's susceptibility to resonance now depends entirely on its accumulated memory. These heat maps reveal the first prediction. The instability threshold is history-dependent. As a system is repeatedly pumped, its threshold for instability decays. A trained system is significantly easier to destabilize than one encountering the same modulation for the first time. The second prediction describes the transition zone. Classical theory assumes a deterministic boundary, but ODTBT predicts a stochastic twist probability. Near threshold, the transition is probabilistic, its width determined by the system's coherence temperature. Finally, it predicts history-dependent attractor selection. When the instability threshold is crossed, the specific post-twist pattern the system adopts correlates perfectly to its phase state at the moment of crossing. Standard Mathieu theory offers no insight into which attractor a system will select after it becomes unstable. These three predictions allow us to uncover mathematically measurable histories in systems where classical physics sees only a blank slate. We can scale this generalized bifurcation down to the precision of photonics, specifically the behavior of optical parametric oscillators. In three-wave mixing, energy conservation requires a single pump photon to split into a signal and an idler photon. For this to work, the waves must satisfy a phase-matching condition, a vector constraint required for a triplet-channel twist. The triplet channel uses crossed fields for directed energy transport, unlike the singlet channel, which describes undirected, phase-incoherent processes like thermal radiation. Because this phase-matched coupling is geometrically directed rather than statistically distributed, it is strictly non-Maxwellian. The triplet channel twist is the structural identity that makes these parametric processes exponentially efficient. While physics theory remained fragmented, Nikola Tesla's engineering bypasses these silos by integrating all three resonance regimes into a single resonant transformer. The primary circuit uses driven resonance via a spark gap. The primary-secondary coupling is parametric, transferring energy through magnetic field modulation without direct force. Finally, the secondary coil enters self-oscillation, sustaining high-voltage streamers through autonomous memory in its own physical geometry. Tesla's 1891 lectures describe these behaviors as aspects of a single phenomenon. The ODTBT grammar provides the formal proof for that intuition, identifying the Tesla coil as a complete resonance hierarchy. We can validate this entire framework using macroscopic cymatics, moving from abstract topology to the laboratory bench. Protocol A demonstrates parametric pattern formation. By modulating drive amplitude at twice the natural frequency, we can observe physical standing waves form at the resonant frequency, despite the lack of a direct drive. Protocol B measures the threshold decay. We can track how the instability boundary shifts over repeated cycles to find the system's memory parameter. If this memory parameter matches the decay rate of driven resonance, it proves that RCR memory is a universal constant across all resonance regimes. Protocol C then tests attractor selection by applying perturbations at specific phases of the oscillation. These protocols convert the theoretical twist bifurcation into a measurable Floquet exponent, providing a concrete path to validation. Driven resonance, parametric resonance, and self-oscillation are not separate physical silos. They are the same memory-bearing truth, unified by the twist.